Next, we are going to look at how to prepare alcohols in the lab. We can prepare alcohols from alkenes, halogenol alkanes, carboxylic acids, as well as carbonyl compounds, which includes aldehydes and ketones. The first reaction is to synthesize alcohols from alkenes, and to do so, we can react the alkene with concentrated sulfuric acid, and then we warm the intermediate with water to form alcohols. This is an example of electrophilic addition reaction. And just as for any reaction involving alkenes, if the alkene is asymmetrical, we need to use Markovnikov's rule to predict the product. And just as a recap, Markovnikov's rule states that when we do electrophilic addition to asymmetrical alkenes, the H, or the electrophile, is going to attach itself to the least substituted carbon. So in this case, the alkene is a terminal alkene. It's a CH2 group, so the H of the water is going to attach itself to the terminal carbon to form a CH3 group, which means that the OH group must be attached to the second carbon. The next reaction is to synthesize alcohol from halogenol alkanes, which we have just learned in the previous chapter. And this is a nucleophilic substitution reaction where the halogenol alkane, either a chloro, a bromo, or an iodoalkane, undergoes nucleophilic substitution with aqueous sodium hydroxide or potassium hydroxide under heating to form alcohols. Take note that the solvent here is important. It must be aqueous sodium hydroxide or potassium hydroxide. If you use ethanolic sodium hydroxide or potassium hydroxide, you will end up getting elimination of hydrogen halide from the halogenol alkane instead. The third reaction is to synthesize alcohols from carboxylic acids, and this is a reduction reaction using a compound called LiAlH4 or lithium aluminum hydride in dry ether as a solvent, and this reaction can only form primary alcohols. Okay, so when we do reactions using LiAlH4, this is a very reactive compound, and it is very picky about the solvents that you can use because, for example, it will react with water in a very vigorous reaction to liberate hydrogen gas. So ether is one of the solvents that can tolerate this LiAlH4. So if we use LiAlH4 as a reducing agent, we will use ether as a solvent to dissolve this compound. And LiAlH4 is a very strong reducing agent, unlike some others which we will see in the next slide. Okay, the final reaction to synthesize alcohols begins with carbonyl compounds, which are aldehydes and ketones. Now, the first difference is that aldehydes and ketones inherently are more reactive than carboxylic acids. So when we reduce aldehydes, it forms primary alcohols, which is the same as carboxylic acids. But over here, there is a wider range of reducing agents which you can use. So same as carboxylic acids, you can use LiAlH4 in dry ether. But since aldehydes are more reactive than carboxylic acids, you can also use a weaker reducing agent, which is called sodium borohydride or NaBH4 in an alcoholic solvent such as methanol. Or you can use hydrogen gas as a reducing agent using a platinum catalyst or a nickel catalyst with heat. Next, ketones. In ketones, the carbonyl group is surrounded by two carbons. So when you reduce ketones, it forms secondary alcohols rather than primary alcohols. And you can use the same reducing agents that you use to reduce aldehydes. Okay, with that, we'll now look at exercise 3 to draw the structure of the compounds formed by reducing the following carbonyl compounds. So first we have this molecule. Now take note here that this molecule contains both aldehyde and alkene. And the reducing agent that you're using is hydrogen gas over a platinum catalyst. And take note that this is able to reduce both the CC double bond as well as the carbonyl group, the aldehyde. So the product will end up with the CC double bond being reduced to a CC single bond, and the aldehyde group, the CHO group, ends up being reduced to a primary alcohol, CH2OH. So where my cursor is at now was the aldehyde group in the reactant, and this CC single bond was the CC double bond in the reactant. Next, we have cyclopentanone being reduced by lithium aluminum hydride in dry ether. So this is actually a secondary, this is a ketone, so it will be reduced to a secondary alcohol. And the product just ends up having a secondary alcohol group. There is one CH bond here that is not being shown in the skeletal structure. And this carbon atom is bonded to two alkyl groups, which is why this is a secondary alcohol.